Okay, we're now recording. Right. So welcome back from full break. We're going to continue with our RSA discussion, right? We have lab today is Thursday. Let's take a look at section table of contents. And we were looking at this. Posted exam grades, so check those if you haven't done so yet. Today we're going to focus on this lab, which is the RSA one. And we had, if I remember last week, we had moved the files, right? So we saw how to download, thanks to Antonio, how to download the files from on our main machine and then move them into the VM. So it's really handy. So we were there essentially, and this should be the lab. So you're learning basically how RSA works. This one is really important because you want to one of the goals here will be to learn how to break RSA, right? Even though you really can't unless you have a very powerful computer, but we're going to learn the techniques. And so understanding the algorithm is key. And this is actually the algorithm that you're going to use to break RSA. Okay, so this is the one that allows you to figure things out once you've broken certain aspects of it. So remember that we're going to do a type of a scavenger hunt by week 12, right? Where you have to, I'm going to hide a secret, I'm going to encrypt it with several techniques, right? And you have to, and it'll have like at least three keys that you need in order for it to be broken. One of the keys that you have to break is going to be based on breaking RSA. Okay. So whatever I encrypt is going to be based on this, and the code that that you will use for that is this code, today's code. Okay. So make sure you understand it, which is actually like a pretty complete implementation of RSA from scratch. So actually every single function is in there, even how to generate prime numbers is there from scratch. So no libraries yet. And so that's what we're going to play with today. So you have, we've done, I'm pretty sure I did problem 2 last Thursday. So today we're going to do problem 3 and problem 4 you guys actually do on your own, right? Where you work with a partner essentially to do all of this. Okay. Hey, how are you? Um, so so now you have completed problem 2. So try using a more advanced implementation. Okay. Because of the complexity of the RSA algorithm, some functions are provided to you, and that's true. So I'm not going to go into all the details of all these functions, but you will see these are the things where in the past examples, I've always given you D or I've given you E, right? And we'll still, in the lecture on Tuesday, still work through some of those techniques by hand, right? Just so that you understand where it's coming from. But here you do have the algorithms. And actually today you will also do a little bit of a example or an experiment, I should say, on performance, right? So the idea that the bigger the key, the slower the RSA algorithm becomes. And you guys will actually be able to see that, right? Because we're going to continue to increase the key until and kind of see how long it's taking to encrypt. So you can see that RSA is a bit much slower in comparison to XOR type tech techniques. So now that you've completed RS problems 1 and 2, try using a more advanced implementation, and some of the functions are provided. For this problem, you will need the source code provided in Brightspace, and you need to write the generate keys function, which is kind of written, and I'll walk you through it, but it's really, what I mean is pay attention to it. Write the generate keys function, and then you need to use all functions available to generate prime numbers, generate the keys, and encrypt and decrypt the message. Right. Once you've completed that on 4, using the code for problem 3, plus any symmetric encryption approach, right? So everyone should understand what I mean by that. Send a message to your partner and achieve confidentiality. This time you must exchange the symmetric keys securely. Do you guys see that? Okay. All right. So this is a problem of public and private key, right? So if you're going to be working with a partner, each partner, Bob and Alice, need to have their own public and private key, right? And they need to decide which keys are needed for this particular problem, given that the goal is to achieve confidentiality. I'm going to be changing this in future weeks, and the goal will be authentication, for instance, and that changes which keys you need to use, right? So you see that. So you want to pay attention to it. So this problem 4 is not as trivial as it sounds, actually. So you got to pay attention to it and think it through. All right, so but let's start with problem 3, right? So that's kind of what the goal of today is just to kind of become accustomed to that script. Make sure you save it on your GitHub or somewhere because you will be using that for the scavenger hunt. Okay? All right, so let's go ahead. Whenever I say break RSA, that's the code that you're gonna need. All right, so let's I need to start the virtual machines. I should have done that. Let's start the VM. Starting the virtual machine here. I think I had 2 versions of the code, but we just need to use one of them. I think one's more complete than the other. Start in a second. Okay, here we are. Let's log in. Okay, so open up the terminal. CD desktop. Okay. Or LS. CD into Volt 2025. ITS 350. There. Right. And I think we were in RSA. Oh, all right. So RSA full code, Scratch, Lab Week, and Toy RSA full code. So let's just look at both. Cat RSA full code. This one. Slash L. Let's try the other one, Scratch. Um, Scratch. Oops. Okay, here we are. Take a look at this one. Yeah, let's either one of these should be fine, I think. So we're gonna get started then. Okay, so remember the idea with this one is RSA is not for encrypting messages, right? Confidentiality, it's for encrypting keys and things like that. But in this example, I'm using a long string, like hello, this is a secret message. All right, but just keep that in mind, all right? Just to make it easier. So this is going to be our message, okay? Um, And I have some functions here, but I'll kind of just go through it slowly. And everything is in here already. Um, right, so let's go to the very top and just kind of go over it. As you can see, not that very long, right? So it's not that long. And this is a very good implementation of the RSA algorithm. Okay, it's got some functions, normal math functions, things like that, random functions that we've been using throughout the semester. Notice here, if you've ever wondered how to generate prime numbers from scratch, here's a function for it. So this is a very nice thing to have available. There's a lot of techniques that are included, right, in a function that generates prime numbers. So we're just going to use it. Notice that in particular, it's called get prime and it takes n, which n is the n bit size of the prime number. So this determines the size. So, and this is going to determine everything else. So the bigger n, the bigger the prime numbers and the bigger everything will be. Okay, so this is one of the functions we need, get prime. This function, notice called the inv over here in the code, is actually the function related to d times e mod phi equal 1. If you remember this in the example that I gave you during the lectures, we talked about how this relationship is what allows you to figure out d. But we need to do it through an algorithm. So this is the algorithm that we're using. This is called the multiplicative inverse, and it uses an algorithm called the extended Euclidean algorithm to solve this problem. So this is the function for that. And notice here that it returns, in particular, the exponent. One thing about this code is it's got like random letters. So I've added notes to it just so that you guys know, oh, this is D, this is E, and so on. Okay? But that's what this function in is for, to find the D component. And here it takes two values, which are actually the E and the phi, because that's the values from this equation, right? So we have E, phi, and then equal 1, we're able to solve for D. Make sense? So that ties into that equation. Okay. Gen RSA, this function actually, I'm going to delete this one. We're just going to write it from scratch, just so that it's easier to visualize. I'm just going to put in a return for now. But this is actually because actually this little function is the one that captures a lot of the algorithm of RSA. So we want to kind of go through it slowly and just make sure that we add all the parameters. All right. So essentially, this is where you generate your public and your private key. Remember that in this exercise, especially for problem number 4, you guys, each of you will have to run this and generate your public and your private keys, okay? And this is the information that you will be using for the key exchange. Additionally, it's got various, and also one thing I'll make a note of here. In the past, I've used this as an exam type thing, so I just jumble the letters. So P and Q is not actually P and Q here. So you have to really pay attention to what should be going into this function instead of what the letters say, okay? Because I've not changed this, but or in this case, it might be P and Q, but I should say in the previous one, it's P and Q. The letters are P and Q, but actually it's E and P. All right, so just pay attention to that. All right. But yeah, and on the practical, it'll be the same. I will give you probably code like this, so you just really need to understand the flow of it. Okay. All right. So this section we usually complete to generate the keys. Then we have several utility functions. So as obviously we're going from strings to integers, things like that. We're going to be printing hexadecimal, etc. So we just need a few helper functions for that. So you don't have to touch these at all. This is text to int, int to text, int to list, list to int, and return the length in bytes of the modulus. So just what is the length of the end parameter. Okay, so just some utility functions. Then, of course, we have our encrypt and decrypt functions, and that is, M to the E mod N, right? And then C to the D mod N, right? So those same functions. Obviously, I wrote those in a very simple way in the first couple of examples. Here, they're written a little bit more robustly, but they are the same. If you notice, the key thing to understand this POW thing. You see this POW here is something to the power of something else. Okay? So these are the functions for encrypting with the public key. Notice here also I've marked the actual parameters. So this is your plain text message going in. This is your E encoding exponent, E exponent, and this is N, which is sometimes referred to as the modulus. Okay, so but that's that equation. So that should be the equation. Let me write that here. That would be the equation that is C, what is it? M to the E mod N, right? So you guys remember that. All right, then we go over here to the next one, and this is the decrypt function, right? And the same thing as before. As you will find out, interestingly, when you see these keys in the decryption part, you actually don't store the D parameter. Instead, you kind of calculate it so you keep the P and the Q. Does that make sense? So you know that we use P and Q to generate N, phi, and from there we find everything, right? We find the D parameters. So here, as you will see later, when we start looking at the OpenSSL examples, when we're looking at the private key of RSA, you will see that actually it's storing the P and Q as well. And that's probably for just efficiency, and it'll process it. All right. And it's not a problem that P and Q are available, because obviously that's the thing you're keeping private, right? So it's the actual secret. You just can't have P and Q in the public key. All right, this equation should be the one that's familiar to you already. So M equal C to the D mod, mod N, right? So the familiar equation as well, and this is the decrypt process. But now this code, obviously you can see while C text everything, this already works for a string, right? So that's why there's more lines of code. You can see it converts a list to integer and so on. For this process, and it's got several techniques. Here's something called the Chinese remainder theorem, right? Several things that were used to solve these problems mathematically. Okay, but it's all implemented in the algorithm. A few additional utility functions. We've got print hex list, so print cipher text in hex. All right, so that can be convenient. So just things that we've used in the past. Okay, and then you can see here, these are the parts that we will rewrite for various things, but we have a few functions here. So we have perform test. Essentially, what we want to do is generate the public and the private key, encrypt something, decrypt something, and then we're going to print it out and so on. So I'll just delete this, and we're going to define it. Okay. We're also, obviously, the process starts with generating the P and Q and just that in. Now this part I'll leave here for now, and that's because I this is the efficiency test. So, or the speed test, let's call it. So it's speed test. So this is something that I want you guys, and essentially what you're doing is you're repeating the process every time, but with a larger seed for the prime numbers. You can see you start at 256, then 512, 1024, 2048. And essentially you should see that the encryption is taking longer to process. Okay, so let's call it speed test, and we're going to leave it there for now. And yeah, again, we can talk about it later. All right, and that's kind of it. So yeah, so let's start with some of the logic here. Uh, we have the message. Separate that out. So we need to implement RSA, and we know that we have a message that you want to send, which can be anything. In this case, this should be the key, of course. So let's go ahead. All right, so I'm just going to manually pick one. So the seat size, in this case, I'm just going to go with 256. Okay, I'm just starting with something smaller. Okay, but here I'll, add a comment that you guys can actually use 512, all the way to 4096 and beyond. Okay, so let's generate some prime numbers. So P and Q. P and Q, these are going to be our prime numbers. So we're just going to use the function get prime. And we're going to specify the seed to be 256 in this case. I'll use seed size actually. Seed size 256. Seed size. And also for this one, get prime seed size. All right. So those are the two first prime numbers, and let's just print them out. So we're going to print P, and we're going to print Q. Should be nothing else. Try it. Okay. Python. All right, so it generated the two prime numbers, but then is not defined. So I must have this function test bit length somewhere. I thought that was disabled, but ah. Let's remove any errors that we have in here. Oh, it's a for loop. Okay, yeah, that's the problem. So for print, and I'm just gonna comment this out. All right. So now it should not give any errors. Right. Okay, so as you can see it print done, that little print done just to make sure there are no errors. But what's important here is I generated two prime numbers. Can you see the prime numbers? Here's one prime number. And here is another prime number. Have you ever seen such large prime numbers before? Right? So maybe when you took math, you were like, that number's too large. And and this is actually just 256, right? So think about it. 512, 1024, 2048, 4096. You see where this is going, right? So these are very, very large prime numbers. The security of RSA depends on this, right? So factorization is the well-known technique that I think we've discussed it already that allows you to break RSA. So we know that to calculate n, what do? We take these two prime numbers and multiply them. That's a very easy operation. The n is in the public key. So an attacker could grab that n. And factorization means what? Reversing that process. So from n going back to these two prime numbers. That is a very hard problem to solve. And that's it. If you right now, go over the weekend and invent some new algorithm that does that, you break the whole of RSA. Do you guys see that? And so that's what quantum computers are trying to do and so on. But anyway, so this code now is, before we were doing 53, 17, or toy numbers. Now we're using more realistic numbers for this process. Okay? All right, so this is really nice. Oh, yeah, please go ahead. Yeah, for sure. And I was going to say, there is actually a lab at the end of the semester. I think it's a bonus lab that I do sometimes. It's called the Big Num Lab. So those are actually even bigger numbers. They're so big in fact, that it has to be written in C, C++ to be more efficient because Python, as you know, is a bit slower. All right. So somebody wanted to see the code. Which part of the code do you want to see? Yeah, I just commented out some things. Okay. All right, so now that I have my two prime numbers, I'm going to have the key. So you guys will be using one of the symmetric keys. Which one? I don't know. Possibly OpenSSL even, right? You don't have to use DAS or AES or CBC, right? The requirement, if you want to use OpenSSL, is fine. But you need to encrypt that key, right? That's the key trick. So maybe you'll be using OpenSSL, AES, CBC, something like that. So I'm going to simulate some key that you would use in OpenSSL, and that's going to be kind of the idea. Okay. So you're done, correct? All right. All right. So now let's continue down here just with the logic as we understand it. So the message here, I'm going to keep it as message, but I'm going to change it to plain message. Just to remember that this is what we are. So this is plain message. All right. And this is going to be equal to just something that looks more like a key. So I'm going to do so 1, 2, 3, 4, 5, 6, 7, 7. Oh, sorry. No. 7, 8, 9, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then ASD. So remember, in the scavenger hunt, if this is, I may not say this, but obviously, if RSA is involved, it's probably encrypting some kind of a key. And I'll try to follow like the correct logic, right? So it would be some kind of a AES key. So here, for instance, we can add a message just saying, notice this is a string, by the way, so it's easy for you to take something from OpenSSL and plug it in here, or should be, because you would just type it up. So I'll just say here, this is where the AES CBC key would go. All right, just as a reminder, this is your key for the key exchange. All right, so we have our message now, and now we're going to proceed to generate our keys. Okay, so that's the next step. So for this, I'm going to use a function, but the keys, if you remember, have to be what? We need the, I'll add as comment, we need the public key, which is what? You should remember E comma N, right? And the private key is going to be D comma N, okay? So that's going to be your two keys. So we're going to have a function that generates these parameters for us. So we call it gen RSA. So it's going to return E comma D comma N, right? So the three parameters that we need to define the public and the private key for Bob, and then the public and the private key for Alice. So this function is gen RSA. Okay, what does gen RSA take? It takes essentially my P comma my Q. So my two prime numbers that my two prime numbers that I just generated. There's some kind of competition going on. All right. So now probably, once we have these, we can start encrypting, but we need to look at gen RSA and just start defining that. But you guys understand a lot of this logic already. All right, so let's go to the function gen, and let me save it actually. So Control F, enter. All right, clear. Now we go back to the script, and let's go to the section called gen RSA, which should be around here. So generate public and private keys. This section to be completed by you guys. So let's 1, 2, 3, 4. All right. So what do we need to do? This is for generating the public and the private key. The first thing we need to do is compute n. So that's going to be P times Q, just like before, P times Q, right? That's what we saw in the logic. And then we also need phi, and that's going to be, which will be equal to P minus 1 times Q minus 1, like that. All right. So these are the two variables that we have defined before. 1, 2, okay. So n is really the really important number, right? And that n sometimes works with a lot with a set of e's, as we will see. So there's a specific rule that says the following. It says if n, and actually let me add this as a next slide. 1, 2, 3, 4. If n, so n value, right? Which in this case, you guys know is a very large number. But if n less than 65,537, okay, then 1, 2, 3, 4, 1, 2, 3, 4. Then essentially you can use E to be 3. Right? So notice that the parameter E is not really it's just a parameter that has to meet the conditions of being of working with these values, with these P and Qs and N. So if N is less than 65,537, then E is equal 3. Okay, 1, 2, 3, 4. And we need to calculate D, and D can be calculated by using that function inv, right? If you remember, inv is the function just above here, the one that uses several algorithms to solve D. Essentially, the one that matches this equation here. D times E mod phi equal 1. Okay? So D, since we have N phi and we have E, we should be able to solve for D. So this, in this case, the parameters that go to inv are E, comma, and phi. Do you guys see that? Make sense? Yeah. All right. So we've done this one now. All right. Then we're going to do the else part. So 1, 2, 3, 4, else. Okay. 1, 2, 3, 4, which is going to be our case because our prime numbers are obviously much bigger than that. So if N is greater than 65,537, then actually 1, 2, 3, 4, E can just simply work B, 65,537. This has been studied quite a lot. It doesn't affect the security of it at all, right? You can just use this as the parameter because everything is tied to N. Remember that, right? So it's N is really the source of everything. All right, so now that we have this value, 65, but it has to be that one, 65,537, we just repeat the process, calculate D for these parameters. Okay, so D is going to be equal to inv, and the parameter we provide is E, comma, phi. Okay, and that's it. That's how you generate the keys. All right, so remember this, going forward for problem 4, you guys have to run this and only run it once. So a common mistake I see students do all the time is they run this function every time. So every time you're doing an encryption, you run it. Every time you're decrypting, you run it. What's the problem with that? Every time you do that, you're creating a new set of keys, right? And so you don't want to do that. You should only run this one time. If you notice, all that this does is it calculates N, it calculates phi, and then essentially in the if statement, we calculate E and D. All this provides is the key. So remember, just run it once. 1, 2, 3, 4. All right. So now we just return the 3 values, E comma D, in the right order. E comma D. And now you have generated your keys. Control X, Y. Okay, saving it, going back to the script. Okay, perfect. So now that we have done this, you have your keys. So let's say you're any questions, guys? You guys have any questions? Yeah. So let's say you are Bob. You need to run this function, save your public and private key, or Alice, save your public and private key. So what I like to do is just create the tuples for these. And then you can usually a good idea is to store them somewhere like in a text file or something like that. So let's create the public key. So I'm just going to say public key, and that's going to be the tuple made up of E, comma, N. And then I'm going to create my corresponding private key, which is going to be D, comma, N. So in a future set of lectures, we're going to repeat this exact same process, but with OpenSSL. It's the same thing. And it'll look different, but we're able to drill down into these parameters as well. All right. So now we probably want to look at them. So let's go ahead and print all these parameters and see what we notice. Good room here. So I'm going to print first n, because we want to see it. Then I'm going to print e, and then I'm going to print b. Okay, so I'm printing these three, and then I'm just going to print the tuple as well. So public key and private footprint. Private key. Okay, there we are. So I think we're at a good point here. We can go ahead and try this. Okay, so it ran well. Let's see what we have here. So we have the original two prime numbers, right? P and Q. Now we multiply them and guess what we get here? Pretty big number, right? That should be your N. Have you ever seen such a large number? All right, so that's N. Then we have our E, which is 65,000. Notice E, the E exponent. And this is actually the D exponent, right? You guys see the difference? Pretty large numbers, okay? And then we have the key, so we have E and N, and then we have D and N. Do you see that? So this constitutes the entire private key, and this is the public key. So for Bob, this is Bob's public key. So this is the thing that Bob makes available to everyone. If you have a website, you put that there in your website. Okay. And then obviously this is the private key. You want to keep this a secret. A secret. Any questions, guys? All right. And then once we complete this exercise, we're going to try all the different, even larger seed sizes. All right. So we've completed that part. Great. On the practical exam, I could give you those numbers just in a text file. So you just have to remember, to grab them and add them into your code here. Okay, so remember that if you're breaking RSA, for instance, you're not going to be calculating P and Q, correct? Instead of calculating P and Q, you're not going to be generating new prime numbers, is what I mean. Instead, you have to get P and Q, the correct P and Q from N. So that's the whole secret. All right, so now that we've completed this part, we can go ahead and do the encryption. Once again, I recommend using Pickle here. You've used it in the past just because that's going to make it easier for you to send things over via email and things like that. All right, so we're going to do that. Let me add just a line here, but the code is running so far. We have a message that I want to encrypt, which is the key. And we can try the other one too. But let's try this one, plain message. So the code works fine. You just have to give it whatever's in that string. So let's create cipher. All right, so we're going to do the encryption. I think the name of the function is encrypt already. Remember, these functions are already built for you. So no, not an issue. So we're going to encrypt the plain message, comma, okay? And what do we need for encrypting? We need the public key. Whose public key? Well, the recipient's public key, right? So in this case, E, comma, N. So here you should not be, if you're the one encrypting, right, you should not be using your ENN. You need to use your partner's ENN. Got it? That's a pretty important thing to understand. All right, so we have the cipher. So let's generate it and print it, and then we can write it to a file. So that, but you guys should know how to do that. So let's try this out. And actually, let me clear the screen. So let's go ahead. All right, so it worked, right? So here it is. This is the cipher, the encrypted message. Okay? Remember why Pickle is so nice? Because it allows you to just save things as they are in memory. So let's go ahead and pickle this. So let's go to Nano. All right, so we're going to save the encrypted key. See, this is the thing now. You can send this key. This is your AES key. So this should be amazing, right? You now have a way of securely exchanging the key, the AES key, which you didn't know how to do before. And all you need is that both parties are using RSA and both parties have a public and a private key. All right, so let's do the pickling. So I'm going to do file X. I'm going to give it some name. So let's do open pickle cipher. Good name. Pickle cipher, and we're going to write bytes. So WB. So write bytes. All right. So pickle dot dump, and we send the cipher into the file X handler. File X. And then we just make sure to close file X. So dot. All right, and that should be it as far as saving your file. So now you can send this to your partner, no problem. All right, let's try this code. Okay, no pickle. Pickle is not defined, so I need to add pickle at the top. So just here, you can just do import pickle. Let's try it again. Perfect. All right, so now we should have our file. And this is really, yeah, so pickle cipher, that should be the encrypted information. We can do cat of pickle, and you can see it's just binary. Pretty good, right? So now let's do the other part of this, which is we want to let's assume you're Bob. So Bob is sending the message to Alice, right? So let's walk through this idea because this is what you guys have to do. Okay. Huh? Yeah, but it's like it froze on me for some reason. Stuck. Pretty strange. Okay. All right. Anyway, so should be working now. Um, so let's go back. So we had the pickle file. We want to decrypt it now, but I was going to walk you through this idea, right? So there's Bob and Alice. So Bob wants to communicate securely, right? And so Bob and Alice are going to use AES CBC to send a secret movie or video clip or something like that. But before that, they need to exchange the key. So we go to the code. So Bob is sending to Alice. So Bob comes in and it's going to use OpenSSL AES. So Bob just decides that this is the key for AES, right? So Bob puts in this key, and now what does Bob need? Does Bob need to run gen RSA? No, right? Very good. Instead, what Bob needs is Bob needs Alice's public key. Got it? Yeah, go ahead, please. Yeah, yes, please, go ahead. Yeah, no, great, thank you. But do you guys understand this part, right? This is key that everyone understands this. Are there any questions on that? Is it clear? Okay, all right. Yeah. All right, great. So yeah, so Bob needs Alice's public key. So you're going to need those values here, right? And to keep it simple, just plug them in here. Alice's key would go here. Get the E and the N that correspond to Alice. All right. And now that you have them, you're going to use them here in the encryption, right? So the E and the N. Now you've encrypted the message to produce the cipher, you pickle it, and you can send it essentially via email to Alice and just tell Alice, hey, Alice, here is the AES key, and I used your public. That's it. So now let's do this part. Let's assume we're Alice, right? And Alice already just needs to have her private key available to do the decryption. And that's it. So that's the whole secret. All right, so let's do that part. So I'm Alice now. I'm decrypting. So the first thing, of course, is I just received this pickle file. So I need to depickle it and make it available. So I'm going to do file Y, equal. Okay, and then I'm going to do open. This is going to be pickle cipher, the name of the file. Pickle cipher. And we're going to say that we're going to read bytes. We are reading bytes. Then I'm just going to say so any name that you want. So from pickle cipher, this is still a cipher. It hasn't been decrypted, so it makes sense. But I'm saying from pickle cipher, you can just use any name that you want. I'm going to do pickle.load, and I load whatever's in file Y. Okay, so now make sure to close file Y, do dot close, and that's it. So now you've reloaded from the file, from the binary file, the cipher, so you can proceed to decrypt it. So we can double check that we have it available, and we can also print it in hexadecimal, which is one of the functions that we have available. So I'm going to go ahead and do print. And let me actually batteries. Okay. So we're going to print the from pickle cipher just to confirm from pickle cipher. And also we're going to try to print it in as a hex list. So I'm going to do print hex list. And this should be this as well. From echo. Right. Okay, so let's go ahead and run these. Okay, no problem. So there's your message. As you can see, it matches exactly. So this is before we pickled it, right? And then after depickling, and it looks, as far as I can tell, exactly the same. But you can corroborate. You can also view it as a hexadecimal, just so that you have another way of looking at it. Send it, etc. Got it? All right. So now that we have this, you've received the message. You're Alice. You're going to use your own private key to decrypt. Okay? And hopefully we will get the exact same secret key. So let's do that last bit of it. So we should get that 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 8, 7, 6, 5, 4, 3, 2, 1 ASD, right? That's the same key. And then you've successfully exchanged your keys. So let's now here, we're gonna create decrypted plane. So we invoke the function decrypt. Notice that, like I said, for the function decrypt, we actually provide the P and the Q. Instead of D and N, we provide essentially D, P, and Q. But that's perfectly fine. And that's exactly how it works in OpenSSL, actually. And I'll demonstrate that next week, probably. So let's add from pickle cipher. And we want the D exponent. So remember, the private key would be DNN, right? That's the private key. But here we store PNQ just because of the way the algorithm works. I think it's a more efficient computation or something. All right. So then let's do print. And let's do decrypted plain. Yeah, and see the message essentially. Okay, so we're going to, and that's it, right? It should be this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 8, 7, 6, 5, 4, 3, 2, 1, ASD. So that's it. That's how you exchange, or how you use asymmetric encryption via the RSA algorithm to exchange your secret key, such as what you would use for AES, block cipher encryption. So SSL, we now start. If you remember at the beginning of the semester, I said I can't really define SSL in a way that the secure sockets layer in a way that you will understand it completely, because I need to define so many other things, right? So we're currently in like week 7 or week 8, and now we start to be able to have all the primitives necessary to define SSL. So now you can see that SSL is actually making use of both of these techniques, right? First of all, you exchange the key via RSA or elliptic curves or one of these asymmetric approaches. And then once the key has been established, you use that key with AES CVC. That's SSL, okay? So SSL is this process of doing all these steps. secure key exchange, and then encryption with the exchange key. Make sense, guys? But we're still not there yet, so I'm just giving you kind of a brief description right now. Later on in the semester, I'll provide a full definition once we've introduced all the ideas. All right, so any questions on this problem? So this is the very basic implementation of this script. Make sure you understand this script really well, as it'll be one of the main things you have to use for the scavenger hunt. All right, so now let's take a look at the next part of this, which is that we want, as I said, I want you guys to use different seeds, right? So you will repeat the process, probably use something longer than that key that I provided, so it's something a bit longer. Keep in mind that RSA is not meant to handle really big things. So if you were to give it a lot of text, it could break, right? Because it's not designed for that. But this should be fine. So we can use this, for instance, plain message is a bit longer, but you can try something even longer just because, you want to see what happens as how long it takes to encrypt given the length of the message and so on. So my suggestion is try different message lengths, right, like this, right? So longer. And you're going to try all the different key sizes. So for instance, from 256, we can go to 512, right? So let's try it. And see it, maybe you notice it took a little bit longer. You can see everything gets bigger. Look at that. Look at these now, right? I think this is N here. Look at the prime numbers, much larger, right? Do you see these big numbers, right? So let's add some separators for some of these. All right, so we print P and Q. So let me just add in here. Print. Okay, then I'm going to print N. Okay, and E doesn't really, it's easy to see, but let's add B. All right. And one more here. All right, good, right? So let's just take a quick look. Clear. Just to see if it's a little bit, see it takes a bit, right? Do you guys notice that? So here's your P, here's your Q. Look at the size of N, pretty big. This is D. And then we have the public and the private keys, right? So you can see that. And you can see also it's encrypting correctly. The text comes out. Now let's try. So as I said, you guys should try this in your own, when you're solving these problems, try different key sizes. So let's try another one. So I'm going to use 1024. Okay, that's the seed for the prime numbers. Oh, sorry. 1000. Taking longer, you see that? So still going. So you see why you definitely don't want to encrypt that movie, right? Your Netflix movie with RSA. RSA is definitely slower than the XOR-based algorithms. So hopefully now it starts to make more sense. For RSA to work, these keys have to be gigantic, but that would just make it impossible to encrypt messages. All right, so let's take a look at the keys now. So that's a pretty big prime number. Think about that. This is another really large prime number. This is your modulus or n, right? This would be, notice that's still the e, and this is your d exponent. So this and that make up the private. Pretty large. All right, let's do one more maybe. So I did 1024. Let's just jump all the way to 4096 and see what happens. You can see it's taking a little bit. Hopefully it'll work. I mean, you could at some point run out of memory. Do you guys understand then this script? So this is going to be the way that I'm going to use it in the scavenger hunt, essentially is I will probably give you the public key somewhere. I could give you, there might be several steps to getting it, but I would give you the public key. Then you grab E and N, right? And you have N. So then later I'm going to show you some techniques to go from N to P and Q, the factorization process. Okay, so there's several ways that we can approach that. One of them is just to assume we have a quantum computer, right? And using something called Shor's algorithm. But we still need to cover that. But just keep that in mind. Essentially, you would take that N, factorize it, get P and Q, and then you just plug in P and Q into this code. So instead of generating the two prime numbers, right, you need to use that P and Q. E will probably be available also, so you can, because I will give you the public key, so you will have the corresponding E as well. Got it? Does that make sense? And from there, just follow the logic of the code to be able to solve it. All right, so hopefully that's clear. But yeah, just keep in mind we're on week 8. So in about 4 weeks, we're going to do the practical. All right, still going. So as you can see, it's very slow when the keys are very large. We may just have to kill it. I'll give it a minute. Still going. All right, so I guess I'm going to have to kill it. Python is a great programming language, but it's not always the fastest language. In fact, essentially Python is just an interface to C, C++, although a lot of the libraries are actually written in C. So obviously, when you're implementing things that have to do with cryptography, you implement at the C level. So for instance, OpenSSL, the program that we've been using throughout the semester, is built on top of a library, libSSL, something like I can't remember exactly. And that library is in C, C++. So at some point in the semester, there will be a C, C++ lab which may be for bonus points. Okay, so with that lab, you would be able to be faster with your encryption. But anyway, it's still going, so I'm gonna kill it so that we can move on. And you can just do this at home, right? At least try. It seems like 496 was too big, so maybe try something a bit smaller. Okay. Yeah, so let's see. All right, so let's take a look at the bright space. All right, so we've completed problem 3. We've gone over the code now, read through it, in more detail. If time permits, we'll go over those ideas of the Chinese remainder theorem or the other algorithm. But essentially, you can read through them if you want right now. So we've completed problem 3. Now, all you have left for the homework assignment to be complete is to do problem 4, right? So in problem 4, you use the code from problem 3 plus any symmetric encryption approach such as OpenSSL, send a message to your partner, and achieve confidentiality. This time, you must exchange the symmetric key securely, okay? My suggestion is use one email to send the key and then another email to send the message so you don't get too confused. You see what I'm saying? But that's it. Do you guys understand? So we did problem 3 more of like the algorithm, the implementation of it, and now problem 4 is more like application, right? How you would use these keys. Any questions, guys? All right, yeah, so work on problem 4. That's it for me on this algorithm. The next time we see it, it'll be if I talk about breaking RSA a little bit, but I assume at this point you guys understood the algorithm, unless you have questions. All right, and then, as I said, problem number 4, work on it with your partner, create a message that you're going to send securely via OpenSSL, but now you can securely exchange the key. All right. All right. So I'll be here so let me end the recording.